Hey folks, so this is an extra question from section 3.9 on related rates, just as promised to give you a little more exposure to the concepts. So the question is, two cars start moving from the same point. One travels south at 60 miles per hour, the other travels west at 25 miles per hour. At what rate is the distance between the cars increasing 2 hours later? Okay, so this is an interesting question. I'm going to start as usual by drawing a picture. So I have two cars that start from the same point. So one goes south. So I have one going south. I'll draw this way. And the other goes west. So one's going west. This. Okay. And so I know some things like speeds, it looks like. So I'm going to immediately start setting up. So maybe this vertical leg I'm going to call A, and this is certainly depending on time. And then this horizontal leg I'll call B, also depends on time. Okay, so what do I know? What I know is the car traveling south is going 60 miles per hour. So dA dt is 60 miles per hour, right? Because it's giving me a speed, a velocity. And I'm going to leave it as a positive number, even though it's pointing down, I'm going to leave it positive because it's increasing, right? This distance is getting longer. So for me, that makes sense. If it's getting longer, I'll make it positive. The other's going west at 25 miles per hour. So this I can write as dB dt equals 25 miles per hour. Okay, and so that's like all I know. Okay, two cars. Okay, I race the distance 2 hours later. So I guess I know something like, I know that the time that has passed is 2 hours, right? From this. So I guess I don't necessarily know how to use that quite yet, but I can write it down as something I know. And what's unknown? So what's unknown is I want to know the distance between the cars. So I guess in my picture, I feel now obligated to sort of connect these 2 points, right? This distance, I can call it C, or I mean, I think that makes sense. And sort of suggesting that I'm noticing it's a triangle. And I want to know the rate at the rate of this distance between cars, how it's increasing 2 hours later. So my unknown, right, is the rate of change of C, right, dC dt, right? The rate of change of the distance. Okay. So it's interesting. I know a bunch of rates, right? I know dA dt, dB dt, but I want to solve for dC dt. Don't know a whole lot else. And I need to know at what rate it's increasing 2 hours later. Okay, so I mean, I don't have a lot else to write down. So I think at this point, I'm going to write down the equation, which feels relevant to me. I'm still looking at sides of a triangle. So the equation I propose to use is Pythagorean theorem. Maybe you already see how I can fill in some of these gaps, but for now, I'm going to just kind of think out loud in my problem solving process. So Pythagorean theorem gives me a squared plus b squared equals c squared. And unlike the example in class, all of these are variables, right? I mean, all of these quantities are changing, so I can't just ignore one of them. I take a derivative. So let me go ahead and take a derivative of both sides, a time derivative, right? So derivative of a squared plus b squared equals derivative of c squared. And because everything is a variable, I need to be really consistent about using my chain rule, right, for every one of these quantities. So a squared becomes 2a times dA dt plus b is also a variable, so I get 2b times dB dt equals, and then derivative of c, similarly 2c times dc dt. Okay, so I know some of these quantities, I know the derivatives, but actually I don't know a, b, or c. I can cancel the 2's, that's fine. but I do need to solve for A, B, and C somehow, right? These are unknowns still. So let me go back up to my picture and figure out, how do I figure out what is the actual A, B, and C? And then the thing I haven't used yet is the time that has passed. So now you ask yourself, well, how do I use this data I haven't used to fill in this picture even more? So what I know is, for example, the car traveling south is going 60 miles per hour and 2 hours have passed. Well, that's important to know, right? If I want to know the distance, it's going to be the rate it was going times the time that's elapsed, right? I mean, alternatively, right, we've used this equation before in chapter 2 when we said the rate is distance over time, right? Because these are all constant rates, I don't have to use like a formal derivative. It's enough to know that, you know, distance equals rate times time is correct for constant rates. So, okay, let's use this formula. The distance then should be, let's do the distance of A. So 2 hours later, the A distance that's been traveled would be 60 times 2, right? Which is 120 miles. Okay, so that's a piece of data I can now add. So A of t at 2 hours, so A of 2 maybe is 120 miles. B, similarly, I can solve. It's 25 miles per hour. Again, 2 hours later, that gives me 50 miles. Okay, great. So I have A squared, I have A, I have B. I can solve for C, right? So now I'm sort of adding all this data. So A is 120, B is 50. And I can solve for C using Pythagorean theorem. So let me sort of on the side here, let's solve for C. So I should have A squared plus B squared equals C squared. Okay. And now this looks a little bit messy. So I'm going to pull out my calculator and type these numbers in to help. So when I get 120 squared plus 50 squared, I get 16,900 equals C squared. And then I want the square root of this quantity, which probably has a nice, yeah, it is a nice square root, yeah. Because, yeah, 169, the square root is 13, and then there's 100 on top of that, so it's 130 is the square root. Okay, not bad. Okay, so C is 130, great. So I filled in a few more pieces of data. Now I'm confident I can plug all this into my equation that I've derived, and I think we can start solving. So plugging in 2 times A, so there was 120 miles, times dA dt was 60, plus 2 times B, B was 50 miles, times dB dt, which was 25, equals 2 times C, we said it was 130, times dC dt. Great. So now my unknown dC dt is the only thing left that's unknown in my equation. I can now just do the algebra to solve. So this looks a little bit messy. I'm trying to find ways to save myself a little bit of heartache here. So I'm going to cancel the 2's everywhere right away. I'm trying to avoid using a calculator if I don't have to. So I'm going to get 120 times 60 plus 50 times 25 equals 130 times dC dt. And now notice I can divide by 10 everywhere if I want to even, so I can make it even a little bit simpler. So divide by 10 on both sides and I get 12 times 60 plus 5 times 25 equals 13 dC dt. The 13 is stuck. So, okay, so now I feel like I have no choice but to actually crank some of these numbers out. That's fine, that's fine. So what is 12 times 60? Well, 12 times 60 looks like it would be 720 plus 5 times 25 is 125 equals 13 dC dt. Now combining some stuff, what do I get? I get 845 over 13 is dC dt. And let's see, I'm not sure if that actually simplifies or not. 845 divided by 13. Oh, it does. So plugging that into my calculator, I found 65 would be our rate of change of C, and that was our unknown. Actually, at what rate's the distance? Yeah, so it's increasing, right, at a rate of 65 miles per hour. Okay. So I like this question. If you compare this to the notes that we took in class, you'll see that this is similar to the boat question we did in class. A key difference is that in this question, all the legs of the triangle are changing. And I actually had to do also an extra step in order to incorporate this how much time had passed data, turning it into actual distances on the triangle itself. Okay, so if you have questions about this, please let me know. I hope this extra example was insightful. Yeah, look forward to working with you more on this.